All right, I'm going to flip around what we did compared to last time. Last time we did the simulation last, and something I had to do the extra video. I don't want to do an extra video, so I'm going to do the simulation stuff first. And since we've been waiting to see Adrian Peterson's simulation, I'm going to go ahead and do that first. So in Lecture A, we're doing more simulation. We're going to review the fundamentals of confidence intervals and hypothesis testing. And in Lecture B, we're going to talk about using confidence intervals for actually doing some hypothesis testing. So we're going to combine the two. We're going to do a two-tailed test with confidence intervals. Talk about some cautions. Talk about something called the power of a test and type 1 and type 2 errors. All right, so let's do the Adrian Peterson stuff. Again, you don't have to know how to do this by any means. This is something that I just kind of had fun with, you might say. Trying to do a simulation myself, and I will, it's more than just about me having fun here. There is a point to this beyond that, and that point is that simulation can be useful, and I want to try to bring that out after I go through what I did. I did keep track of, I did go back to 2012 and record all his rushes. So each one of these numbers that you see here, 4, 9, -2, -1, those are how many yards he got in each rush for that entire season. Okay, I went through Control F to find his name was helpful in finding all his rushes. It only took me a couple hours to do this actually, and I thought it was time well spent actually. I was worried that was going to take me 5 or 6 hours, but it only took me a couple hours to find all this data and record it. Anyway, those are his rushes for the 2012 season when he got 2,097 yards total, which is the second most in history after Eric Dickerson about 30 years ago. You can find, based on this information, the 5-number summary, and you can make a box plot. And when you look at a box plot like this vertically, you have to realize you're going to look at it with your head sideways. The numbers are going up here if you turn your head sideways like this, and you see it's very much right skewed, okay? Which should make good sense for a running back. Most of their rushes are going to be less than, say, 5 or 6 yards, but a very few were pretty long, like 82 yards I think was the long. Yeah, that's the maximum. The third quartile is 6, the median was 3, the first quartile was 1, and the minimum was -6. He lost 6 yards on one rush. You can also calculate the mean and standard deviation. He averaged a little over 6 yards a carry, which is amazing, and had a standard deviation of 11.2 yards. You can make what I call a rush series graph that's analogous to a time series graph, showing the ups and downs of each rush. The first one was like about 4 yards, the second one was about 9 yards, the third one was like -2 or something, showing his rush yardage in terms of how many rushes he had. And one interesting thing that I see in this is that in the first 150 rushes or so, his output, his yards, was fairly ordinary. But then all of a sudden, about rush 150, then he had a bunch of really long ones the rest of the season. And that's what contributed in a big way to his rushing total. So that's kind of an interesting thing for that reason. At the end of the season, he sort of went back down again. Although his total per games, he was pretty consistent here still, and he still got like close to 200 yards, I think, in one more game near the end of the season. You can make a histogram of this. There's the distribution. It's right skewed as well. And actually, if you did graph some Poisson distributions, I don't know that we graphed one of those in class. I might have shown you a graph. It kind of looks like it might follow a Poisson distribution. I tried fitting it to a Poisson distribution where, I think down here, and it fits. It's actually not a Poisson distribution. It's a Poisson distribution shifted to the left by 6 spots since his minimum rush was -6 yards. And it fits it halfway decently, but there's a big flaw in it. And the flaw is it misses all the high outliers. It goes down too fast. And so you really don't want to use a Poisson distribution. So what do? I ended up creating what you might call a user-defined distribution. I created a piecewise function that approximated the distribution well. I first made the distribution, instead of a histogram, I made a line graph for the distribution. Then I created a function, let's see, where was it? That's not it. Right here, G, I called it. It's what's called a piecewise function, and I tried to use G as to be a simple function that sort of models the pattern. It doesn't do it perfectly, and it's not a density curve because the area under it is not 1, and if you know any calculus, that's an integral sign to emphasize the area is not 1. And so what I did was to create my final model, my final piecewise function is I divided that function by the area under the graph to create a new function whose area was approximately 1 so that I could use it as a density curve. Blah, blah, blah. I can compare the graphs. I can create a probability distribution. Check and see if the graph matches. Calculate the mean and standard deviation. It was a little high. That's a little bit high for the mean and standard deviation. So this is not going to be a perfect model by any means. But to get to the crux of the matter, where you actually do the simulation, this Mathematica program allows me now to do simulated seasons. You have 348 rushes. I can enter this code, and there's a simulated season of 348 rushes. If I re-enter it again, it produces a new simulated season of 348 rushes, etc. I can just keep entering this over and over and get more and more simulated seasons, or I can make an animation allowing me to change the simulations. And I can make graphs of various simulated seasons. Okay? Each one of those represents some fictitious season that didn't actually happen, but we would be consistent with what he did that year. I might want to also make, let's see. Yeah, this is where it gets extra cool to me. I could make simulated seasons, for example, 40 simulated seasons, and see what happens in each of those 40 seasons. And here's where it's really cool, because you can try to, if your model is accurate, you can assess how often, if he was rushing that well in a given season, might he get above 2,500 yards, which would be unbelievable. And if my model was right, which is not, again, it was a little bit too high with the mean, I do see at least one season where he's above 2,500 yards. Actually, two, there's another one. And in only a few of those seasons is he below 2,000 yards. I could make a graph of a series of simulated seasons, a histogram, and you can see these are a bunch of simulated seasons, 40 seasons in fact, and then in the majority is about 2,000 yards. Now again, my model's not perfect because the average and standard deviation came out too high. I can try to modify the model to make that better. But if it was accurate, that's pretty amazing. You could say, if he rushes just like he did in 2012, you can expect him to get about 2,000 yards, for example, the majority of the time. Now that doesn't mean he's going to rush as well as he did in 2012, so it could be a moot point in that sense. But it's fun to think about. You can do it for games. He averaged 22 rushes per game, and so you can do simulated games. Like that game, he got 120 yards. Here's a bunch of games, 16 games in fact, pretending it's 22 rushes per game. Actually, okay, don't worry about this. This code is not quite right, but I think this works simulating 16 games in a season. Why is this useful? Besides it being fun for me, why might this be useful for somebody? Here's an indication of how it can be useful. You might be a coach on a football team, for example, and you might wonder, okay, how often should we have our running back run plays? Should we have them run 50% of the time, 25% of the time? And how often should we pass? And you can make assumptions about that. And then you could try to combine that information and do simulations of simulated games and see how well your offense does overall. And the benefit of putting it in computer code is that you can make tweaks really easily. You could say, okay, in this game I'm going to pretend my running back runs 50% of the time. And now I'm going to tweak it and pretend the running back runs 25% of the time, and let's see what happens. How does it affect the offense? How does it affect the production? How does it affect how much you score? You could even bring the downs into play, first, second, third, fourth down. It'd be more complicated. But if you try to imagine scenarios playing out and being able to tweak things easily on a computer, that could be really useful. Okay? And that's the main point I'm trying to get to here ultimately. The simulation can be useful for playing out possible scenarios. So even though it's complicated and you don't understand the math here, I hope you see the big picture point. Now, if you ever did simulations beyond basic spreadsheet simulations in your job, probably it would be with software somebody else created. But maybe it's software similar to this in the background that you don't see and don't have to worry about. And you get the joy of tweaking it a little bit to see what happens. And in a business setting, what might be applications? It could be applications based on, you know, how much do you spend on advertising? You could have some models that say when we spend so much on advertising, we can expect so much revenue and so much expenses. And then you try to tweak the amount of advertising to see if your revenue goes up faster than your expenses do. Okay? How do consumers react? Those kinds of things, based on data that you gathered in the past, could be things that you can tweak in your computer programs to try to see what happens and make decisions. How much should we spend on advertising, for example? Okay? Some big picture ideas here. Lots of big picture ideas here today. They're all important, though. I get excited about simulation. This is just fun for me. Okay? Maybe it's not fun for you, but I hope these spreadsheet simulations are at least kind of interesting to you. Let's go ahead and do a spreadsheet simulation now again. This will be like the next electronic assignment. What we're about to do is pretty similar to the one you turned in today, except instead of a binomial random variable, we're going to use a Poisson, which again, you should know the formula for the quiz, so I hope you studied that. Let's go ahead and imagine an application here. Okay? I'm going to do a Poisson distribution with a small mean here. I picked the mean to be pretty small, 0.8, less than 1. What might an application of such a distribution be? Remember, Poisson counts occurrences of things just like binomial distributions do, except there's no theoretical upper limit. You're counting things in a certain amount of time, perhaps, or in a certain length, distance. An application I imagine here, and this would be important, for example, for insurance companies, is maybe you're counting the number of hurricanes, official hurricanes, that hit the coast of Texas per year. Okay? It's conceivable to me, in fact I talked to some actuaries who talked about this, that they might use a Poisson model for that, to count how many hurricanes to expect to hit, say, Texas or Florida in a given year. Official hurricanes. And maybe the mean based on past data is 0.8. 0.8 hurricanes per year. Maybe they gathered data from the past 100 years and 80 hurricanes hit the coast of Texas in the past 100 years. That would be an average of 0.8 hurricanes per year. Poisson would be certainly the simplest kind of model you could use for that. And in fact, they do use it, at least as first approximations. Once again, just like the binomial distribution, there's a built-in function on the spreadsheet that will calculate Poisson probabilities. Not Poisson, Poisson. All right? It's got 3 entries. X is the value of k, the different values x can take. X is the random variable, counting the number of hurricanes, say, in a year. K is the different values that x can take. So the first thing is the k value there from in this first cell, cell B4 will be where that is. Comma, the mean. The mean is in cell B1, any dollar signs because I want that to be the fixed reference. Then is it cumulative or not? You put false or true. So in this first spot, it's going to be a B4. Then put a comma, $B, $1, because the mean is in cell B1 and I want to keep it there. Then put false. Doesn't matter whether you capitalize it or not. For a Poisson distribution with a mean of 0.8, you can see the answer here. The probability that x is going to be 0 is about 0.449. If truly, based on past data, 80 hurricanes have hit the coast of Texas in the past 100 years, for an average of 0.8 per year, you would expect about a 45% chance in any given year that a hurricane will hit. That's the simplest kind of model. It doesn't take into account things like El Nino, if you know what that is, which does affect the weather greatly. If climate change is going on, it doesn't necessarily take that into account, okay? It's just the simplest model based on past data. I can copy and paste this, see the other probabilities. Probability of 1 hitting is about 36%. The probability of 2 hitting is about 14%. A probability of 3 hitting is about 4%. probability of 4 hitting in 1 year is less than 1%. We're getting down pretty close to a probability of 0. Is the probability ever 0? Not with this model. The probability of there being 100 hurricanes, according to this model, is a very super tiny positive number. Okay, so tiny it's almost unimaginable. It's technically not 0. However, for all practical purposes, you can treat it as 0. Let's look at the cumulative now. The only difference here is put a true in the end instead of a false. What's wrong here? I got the wrong cell for the mean here, B1. Okay, that's better. That first number is the same, because the probability of x being less than or equal to 0 is the same as the probability that x equals 0, because it can't be negative. And it has to be a whole number. But with this next one, it's going to be different. This number, 0.81, is 0.45 plus 0.36. This next number, 0.95, is 0.81 plus 0.14. You're essentially adding these up to get this, but you can also do it with the true instead of the false. Keep going. We're approaching 1. Does it ever equal 1? Not technically, but close enough. And in fact, now we're going to round these to 3 places after the decimal, just like we did before. Go up here, decrease the decimal places until it's 3 places after the decimal, like that. Okay? I made mu small so we don't have to do too many cases, so when we do our equals if, we don't have too many things to do. We're going to only go up to effectively 5 as our last possible likely value of x. Because after that point, it's so close to 1. We'll treat this as the last possible likely value of x, ignoring everything else. We can use RANDBETWEEN, just look at, like before, RANDBETWEEN 1 through 1,000. Oops, what happened there? Oops, typed it wrong. No colon, but a comma instead. Do this over and over again. I have 200 times here. Okay, so 200 simulated years for Texas, maybe 200 years in the future. What's the value of x here is, again, the trickiest part. I want to base what I do here off of these numbers, times 1,000. This is the tricky part where I need the if over and over and over again. How does if work? You put a condition in the first input. It's called a logical expression there. We're looking at the RANDBETWEEN, which is in cell G4. Is that less than or equal to first, to start with, this number times 1,000, 449. The idea is if RANDBETWEEN gives you an output between 1 and 449, that represents getting 0 hurricanes that year, because the probability of 0 hurricanes was 449, 0.449. There's 449 numbers from 1 to 449 out of 1,000 numbers that RANDBETWEEN could give us. There's a 0.449 chance of getting one of the whole numbers between 1 and 449 inclusive. So for those, if that's true, you put a comma here, then put 0. 0. Look up here. That represents getting 0 hurricanes. What if that doesn't happen? What if RANDBETWEEN is bigger than 449? Then do something else. It would be simple if I just put like a 1, so there's only 0 or 1 hurricane, but there could be up to 5. So I have to keep going with the ifs. This if it is reached, is already in the case where the output of RANDBETWEEN is bigger than 449. Because if I don't get in that case, I don't get an output of 0, I get an output of something else. So by putting it less than or equal to 809 here, I'm really considering outputs of RANDBETWEEN that are between 450 and 809 inclusive. And if that happens, that's the 1 hurricane row. I want the output to be 1. But remember, we keep going until we get to 5 possible hurricanes, so I use if again. What should I put G4 is less than or equal to there. Somewhere over here times 1,000. 953, yeah. That's going to represent getting 2 hurricanes in the year. The next one, 991, represents getting 3. It's easy to type this wrong, like make a mistake and forget a comma or something. The next one, 999, that represents getting 4 hurricanes. I don't need any more ifs because the only other option I'm going to consider is getting 5 hurricanes. There we go, I put a 5. Now close off all your ifs. 1, 2, 3, 4, 5 of them. Is this doing what I want it to do? Well, in this first case, RAND between is 490. That's representing 1 hurricane. I got 1. Copy and paste this. Let's check if it's working for some other ones. In this case, RAND between was 958. That isn't the case with 3. 0, 1, 2, 3. In the first case, 919. That is representing 2 hurricanes. 0, 1, 2. Etc. 584 represents getting 1 hurricane. 0, 1. We're in this case. 74 represents getting 0 hurricanes. We're in the first case. I can do this over and over and over again. $200 times, and this, you're doing exactly what I'm doing on the, I hate when that happens. You're doing exactly what I'm doing on your assignment. I am essentially showing you how to do the assignment here, but I do want you to strive to do your best to understand it. So we got a bunch of 0s through 5s there. Now I can go and make a table. One of the different values of x, 0, 1, 2, 3, 4, 5, which is the number of hurricanes in a year, say. How many times did each observation occur? Now I can use equals COUNTIF. I'm looking at column H, H4 through H203. Now do equals COUNTIF. H4 through H203. What's the criterion here? For this first row, it's equals 0. I'm counting the number of zeros. Because it's right next to the 0. That's the reason I'm doing that. How many times does 0 occur? It should occur about 45% of the time, right? 45% was the approximate probability of getting 0 hurricanes. 45% of 200 is 90. Should get close to 90 here. 89 shows you the answer, but when I enter it, it'll be different probably. 95. Do the same thing for these other ones, but put a different equals. This one is equals 1 in quotes. 72, etc. Nope, you can't copy and paste here because the equal part changes. And I don't know of any way to fix that. Maybe there is a way. Almost done here. I hope I typed everything right. Okay? And then you can convert those to proportions by dividing them by 200. Finally, I'm going to want you to make a graph, just like you did for today's assignment. 2 graphs, in fact. One where you're graphing the theoretical probabilities up through k equals 5, bar chart, and one where you're graphing these proportions that you get from the simulation. They shouldn't necessarily be exactly the same, but they should be somewhat similar, illustrating the idea of a probability distribution. Is this useful? I claim it is. I claim the simulation, for one thing, it helps you understand probability better. For another thing, it can give you ideas of what kinds of things to expect. Besides the probabilities themselves, for example, it could, if you apply the simulation over and over and over again, give you expectations about how often you get 0 hurricanes in a given year, say 3 years in a row. If not occurring here, that's 2 years in a row. It's not occurring there, that's 2 years in a row. Do we ever see it occurring 3 years in a row? Yeah, right there. There's 0 hurricanes are occurring 3 years in a row. Are there other spots? Yeah, wow, there's 5 years in a row with 0 hurricanes. It can give you more detail than the probability distribution itself does about expectations. And that would be important to an insurance company as far as setting their prices, their premiums, and figuring out how much they're going to have to pay out in benefits. These are useful things. All right, that's all I want to do with simulation today. I think the hard simulations, these are the hardest simulations, we're probably done with. The simulations we're going to do from now on are going to be a bit easier because we don't have to worry about the RANDBETWEEN, I think, mostly. We're going to simulate normal distributions mostly to come, and something else called a t-distribution. And the way to do it will be a little simpler because you won't have to worry about the RANDBETWEEN. You probably won't have to worry about the ifs. We'll still use COUNTIF probably, but they will be a little simpler from now on. Okay? All right, in the time we have remaining before the quiz, let's review the basics about hypothesis, confidence intervals and hypothesis testing. First of all, here's the general formula for a level C confidence interval to estimate a population mean. Remind yourselves about what this is for. We are trying to estimate a population mean mu. Instead of taking our 1-point estimate, x bar, we're expanding it to an interval estimate, x bar plus or minus m. M is called the margin of error. The formula for the margin of error takes this form. This is a special value of z that depends on the confidence level, depends on c. And this number right there, sigma over square root of n, that is sigma sub x bar. That is the standard deviation of the sampling distribution of x bar. This is unrealistic in chapter 6 because we're assuming we know sigma when in real life that would be rare, if ever, really. Okay? Because it makes the calculation simple. So you should know how to calculate that. You should know that z star comes from the bottom of the t-distribution table. You don't need to memorize these numbers. If you need one of these numbers on the quiz or test, I will give them to you, but you should understand that if you want a 95% confidence interval, you'd use 1.96. If you want a 99% confidence interval, you'd use 2.576 for z star, etc. You should understand that basic principle. You should also understand how to interpret it. It's kind of technical. The confidence level, for example, 95%, could be interpreted as a probability before you actually do the sampling. I'm about to sample. I'm going to calculate a 95% confidence interval. I'm doing simple random sampling, which is the assumption. That's what makes these models valid. Otherwise, it's not valid. It can be biased. I'm about to do a simple random sample of a certain size. I wonder what the chances are that it will contain the true population mean mu, my interval. If you're going to do a 95% confidence interval, you could assess that as a probability ahead of time. However, once you've done the interval, then you don't want to think of it as a probability, technically speaking. Although betting-wise, maybe you could. But technically speaking, you don't want to think of it as a probability anymore. So you use this new word, confidence. We're 95% confident that the interval contains mu. True unknown population mean. A little bit more rigorously, and if we did repeated simple random samples of the same size from the same population and calculated many, many different confidence intervals, and you would get a bunch of different confidence intervals. The confidence level reflects how often the various intervals would capture the true parameter value. If you're doing 95% confidence intervals, it's going to be captured about 95% of the time. In real life situations, nobody really knows mu. And usually it's even unknowable. You're trying to estimate And that means, as a consequence, you don't know whether your one confidence interval actually contains u or not. So, but there's nothing that can be done. This is the best that you can do. That might feel unsatisfying, but it's the best you can do. Here are some common misconceptions about the meaning of confidence intervals. Again, like I mentioned a minute ago, after sampling, they should technically not be thought of in terms of probabilities, and thus we use the new word confidence. The higher the confidence level, the more confident we are they contain the population parameter. A 95% confidence interval does not capture 95% of the population data. That's not what it's about. So realize that. Or the sample data, for that matter. We're 95% confident it contains the true parameter value that we seek to estimate. Mean, for example. A confidence interval is not the final word on the value. For one thing, it might not contain u, and you might want to do other studies to try to pin u down more precisely. So those are some basic misconceptions people sometimes have. I'm trying to correct them there. What about hypothesis testing, the basics? Again, don't write this down. We're just going quick because we're going to take a quiz here pretty soon. The null hypothesis, you should know for the quiz and future quizzes that it's oftentimes a statement of no effect or no difference. Okay, you're changing something, you're wondering if the population parameter is changing, or you're considering some subset of the original population, you're wondering if it's a different value for the population parameter. The null says, no, it's the same as it was before. Okay, that's a common way to think about the null. You should know what the p-value of a test is. This is a very general statement here. It's a probability, for one thing. It's the probability of observing the data you observe and getting the x bar you observe, you calculate, and the z you calculate if you assume the null is true. Say that again. It's the probability of observing what you actually observe from your sample if you assume the null is true. If it's a small probability, that means you think probably the null is false then. If you've got a very small p-value, that's strong evidence against the null. So very small chance of observing what you actually observed. If you assume the null is true, therefore we think the null is not true, you reject it. That's the basic statistical logic. That's key to everything else for the course. The level of significance sets the standard of strength of evidence that's required to reject the null. The lower alpha is, the higher the strength of the evidence you need before you're going to reject the null. It's an inverse kind of relationship. Smaller alpha means your p-value is going to have to be smaller than alpha before you reject it, so that's going to be harder to happen, even if the null is false. In effect, you are reducing your chance of incorrectly rejecting the null when it's true. Alpha can be thought of as a probability that way. Those are the basics. We'll talk about more after the quiz.